Hi everyone, and welcome to part 4 of our Unit 8 lecture series. Our learning objectives for this section are to explain the relationship between surface water and groundwater in an unconfined aquifer and the relationship to local streams, and to explain the difference between regional and local groundwater systems. Over large spatial scales, the water table can roughly follow the topography. It will tend to be a higher elevation further away from surface water bodies and at a lower elevation where groundwater discharges to surface water, either in a stream or a lake. At this groundwater-surface water interface, the water table will be even with the elevation of the water in the stream or the lake. When humans install pumping wells, it draws down the local water table in a cone of depression around the pumping well, shown here. This can actually cause a flow reversal, so the groundwater flow goes towards the well, reducing groundwater flow into the adjacent receiving stream. In addition to variation in space, the water table also can go up and down over time. Recharge is the process by which water is added to the zone of saturation. It occurs when moisture percolates below the zone of soil water. The illustration to the right shows the water table elevation for 3 wells installed in the same field. The water table rises during periods of recharge. This means that the amount of water entering the saturated zone as percolation below the soil water zone is greater than the groundwater flow out of the region. During periods of discharge, the water table falls, indicating a negative change in storage in the system. During these periods, the groundwater flow out of the aquifer, QG, exceeds the percolation, G, into the saturated zone. These periods of recharge and discharge to the groundwater flow system also influence stream flow response. This graph shows observed stream flow for Little Weah Creek, near campus in Indiana. This red line separating the hydrograph gives a rough illustration of the contribution of storm flow coming from overland flow and interflow pathways, and the base flow coming from groundwater sources. Following recharge of the groundwater aquifer, groundwater discharges to the creek, increasing the base flow rate. It is possible for the water table to fall until it is no longer above the bottom of the stream in valley bottoms. This results in our intermittent streams that dry up during the summer. They are no longer supported by groundwater flow because the groundwater level is below the bottom of the stream. This is very similar to the concept of gaining and losing streams. Gaining streams receive groundwater flow from their surroundings, and as a result, stream discharge increases as you move downstream in the channel network. In a losing stream, the groundwater table is below the elevation of the stream bed, and water from the river can infiltrate through the stream bed to recharge the underlying groundwater aquifer. Losing and gaining streams can change seasonally, in the case of intermittent streams that dry up in the summer. But it can also happen perennially when the regional aquifer is well below the stream elevation. This happens locally in the Wabash Valley, where the lowest reaches of many tributaries to the Wabash become losing streams along their lower reaches, as they are running over the alluvium of the Wabash Valley, as illustrated here, in order to get to the Wabash River. Our previous examples have concentrated on the dynamics of near-surface groundwater flow. If we expand our view to look deeper, we can see that in some regions, groundwater flow systems can be very complex and extend much deeper below the land surface. In such areas, regional groundwater flow systems can develop that take water out of local watersheds. So our local watersheds are shown up here with a stream system and local watershed divides. Our vertical scale is greatly expanded and is extending several hundred meters into the subsurface. Over here, we have a Great Lake, such as Lake Michigan. So we're going to zoom in on one of these local watersheds. If we zoom in on one portion of this regional flow picture, we can see that for the cross-section of an individual watershed, the groundwater flow lines go to the local stream, as we have seen previously, as indicated by this number 1. But we can see that there's an additional flow line, shown here, that extends below the local stream. Water following this flow path is lost from the local watershed and will instead discharge miles away in another river, or in this case, in a Great Lake. Regional groundwater flow systems are more likely to occur in areas with very deep deposits and gentle topographic relief. When we construct a watershed water balance, if we do not include a groundwater loss term, we are assuming that only local groundwater flow exists. This concludes our final lecture of Unit 8. You are now ready to tackle homework assignment 8.